Okay, so good afternoon, everyone, and welcome to today's Nastran In-CAD session. My name is Matthew McKnight, and I'm going to be going over buckling verification using the In-CAD product. A little about myself. There's my contact details if you need to contact me after the session. If you've got any further questions and follow-up you'd like me to do in regards to this or any of our other products based out of the Melbourne, Australia office. So feel free to reach out to me if you have any questions. Otherwise, a quick look at our agenda today. So we'll be looking at what is buckling, how do we analyze buckling, looking at the workflows, limitations and advantages of analyzing buckling. We'll look at a quick example, draw some conclusions, and then point you in the direction of some further reading. Otherwise, let's get stuck into the content today. So firstly, what is buckling? So buckling is a failure mode quite commonly experienced for manufactured mechanical components. If we look at Euler's buckling equation, you can see there that it's a function of a couple of different parameters, in particular the stiffness of the part, which is a key to understanding the buckling criteria of components, length, which is the unsupported length of the geometry, and then we have some typical properties such as modulus of elasticity and the minimum moment of inertia. So these are the real critical elements in understanding buckling of our designs. Where today we're going to be looking at the two most common solutions for analyzing it. We're going to be looking at the linear, which is looks at the eigenvalue, and nonlinear analysis of buckling. So how do we analyze buckling? Well, let's have a quick look at firstly the typical workflow that you can use when analyzing structures for buckling. And we advise starting with a linear buckling analysis to get a buckling load. The buckling load can then be used in a linear static stress analysis to understand some of the stresses in our design. So from this, the linear static stress analysis can determine whether a nonlinear buckling analysis is absolutely required. And then we advise doing a nonlinear analysis as it can improve the accuracy of your buckling load prediction. So when you're doing a linear buckling analysis, one of the things that you're going to obtain is the critical buckling value. You'll also get the buckling mode shape, so we're going to see how the part deforms. And we'll also get to see the stress and displacement. Note, however, though, that these values are not quantitative and are only relative to one another. Finally, the values are non-conservative, so be aware of that. For a simple design like in our example today, the results can be accurate. That being said, you can find that as the complexity of the parts and the geometry that you're analyzing increases, you'll see that the value can become inaccurate and hence the need for nonlinear analysis when comparing with linear analysis. So why conduct a linear static analysis in the first place? Well, it'll help us determine whether there are any material nonlinearities we need to account for. And it's also a quick and easy to do, and it also helps to determine where you want to go in the future. A nonlinear analysis can be a bit more challenging to conduct. It's going to take into account both geometric and material nonlinearities, and we've talked about some of those in previous webinars, but it's also going to give you the post-buckling response. So what happens after the part buckles? What's the geometry, the reaction of the geometry post-buckling? And this is something that you obviously can't get from a linear analysis. So you'll be able to see what's happening to the design throughout that buckling process. So the structure is buckled, what's going to happen is really what we're considering with a nonlinear analysis. So let's look at setting up each of these types of analysis. Firstly, with a linear analysis, we have limited output. It's traditionally non-conservative, and as with all buckling solutions, the results are mesh sensitive. You can see here in the plot that as the element count drops, the eigenvalue increases. So consider your mesh when running analysis and look for a converging result, typical of most simulation results you're running. And remember, we're not taking into account any nonlinear material behavior as opposed to a nonlinear study where we would be. So if we look at the nonlinear analysis, obviously now we're considering nonlinear material and geometric response. So we're considering the change in the shape and stiffness of our part. We also need to consider how we're applying the loads as well. There can be issues obtaining convergence, hence the need to start with a linear analysis. And again, this is mesh sensitive. You can get improved accuracy over linear analysis types, but we also need some type of imperfection in the analysis, and we'll highlight this today in the example that we work through. So what do we mean by imperfections? Well, these might include the likes of deformed geometry where we'll create some sort of irregularity in the model. We can modify material properties in a specific area or section of the model, slightly lowering the stiffness value. We can also modify the mesh, though this can be difficult in certain instances. One of the easiest methods is to apply what's called a kick load, which is an out-of-plane load that will result in a small amount of deformation and help instigate buckling. The kick load is one of the simplest and easiest to apply in this instance, and one of our preferred methods. Lastly, deleting elements is another alternative. So, let's have a look at a practical example of how we can apply buckling or run buckling analysis, and let's have a quick look at a simple part that we've got. So we've got a straight bar that is 250 millimeters long, and it's got a diameter of 12.5 millimeters. It's fixed at one end and free at the other. So we'll assume it's in a vertical position. It's maybe bolted or welded, or it's got a fixed rigid constraint at the bottom, meaning it can't move, but it is free to move at the other end. We've applied a 10 kilonewton load, a compressive load, actually along the part, vertically down. And we're assuming that it's a material, it doesn't really matter in this case, but it's probably a material that's reasonably similar to an alloy steel. So let's jump into Inventor and have a quick look at how this works. So we've got a bar that's been set up. Now we could run the analysis on the bar using mesh elements, a solid mesh, but what I want to do is actually represent this in a slightly different way and represent it as a line element. So in this case, there's really even no need to create the geometry, and we're often referred to in a lot of these Nastran In-CAD webinars where we really want to simplify our geometry, take it back to basics so we can analyze much earlier in the design process. And this is no different with buckling analysis. So you can represent your geometry as sketch elements and then assign geometry to them. And that's exactly what we've done here. So I've got a simple sketch that's 250 mil long on a plane, and that's really all we need. So if I go inside my Nastran In-CAD environment, you'll see that I've set up a number of studies that will step us through the typical workflow that we would use in this case. So in this instance, I'm going to highlight really what we've done. So the first study that you would typically run is a linear buckling analysis. And there's really nothing special about setting this buckling study up. There is an option inside of your study type for linear buckling, and that's all we've selected here. We haven't changed any of our output controls, the output sets or anything like that. We've just set a simple linear buckling analysis. And like we've said, working from left to right on the ribbon bar or top to bottom in the tree helps us work through sequentially in the bits and pieces that are required of our studies. The next that I've done is set up a material. I've just called it buckling material, and we've used this for all of our buckling studies. Like I said before, it's It's got a 200 gigapascal elastic modulus. And Poisson's ratio is just set to 0.3. There's no other mechanical requirements. There's no other thermal properties that are required of this, and that's all we really need in this instance to be able to analyze our part. We have assigned a physical property, so if I look at that physical property, you can see it here. So by default, it's most likely going to come in as a solid element, but we've switched this to a line element. We've used bar elements as the element type. I've assigned the material that I want to use, in this case the buckling material that we'd previously set up, and I've chosen the sketch segment that I want to associate this geometry. So if you've got a complex structure with lots of sketch segments, you can go through and choose certain segments to have certain properties or certain materials. You can go and adjust neutral axes, rotation of the sections and the likes. The only other thing I've really done is gone in and changed the input type to cross-section, and I've then defined what that cross-section is. And in this case, I can go and choose from any number of predefined typical cross-sections that I want. So say if I wanted a T-lintel or a box section, that I can. In this case, I've simply chosen a rod, and I've inputted the radius. So that's the only real trick here, is that note that though it sort of has the diameter call out here, it's actually saying 2 times dim1, and dim1 is therefore a radius dimension. So half of our 15 millimeters, sorry, 12.5 millimeters gives us our 6.25 radius. Apart from that, there's really nothing else that we need to do. We've assigned our, our physical property and our material. We can then move on to the subcases that we've created. In this case, because it's a buckling analysis, it will automatically create 2 subcases. They're basically set up identical to one another. In this case, I've applied a buckling load, a linear buckling load, and that buckling load is at the end point of our line element, and it's this compressive 10 kilonewton load that we were talking about before. It's a simple force. There's nothing really complex about that. It could be a combination of forces if you knew that, and it could be multiple forces as well. And we also have a fixed constraint here. Let's just have a quick look at that. So there's nothing complex about the way that this has been defined. A simple fixed constraint at the other end of the beam, restricting rotations and translations at that point. Finally, the one thing that I have changed is in mesh settings, and you can activate, go to the mesh settings by editing the mesh. We have split the element size. So by default, this may have come in as 5 or 10 millimeters or thereabouts. I've evenly spaced these along to have about 10 elements for the beam length. In this case, it's such a simple example that it won't be critical, but you may find that your mesh density, as we pointed out, can have some influence on your results. So be aware that you may have to go in here and fine-tune this based on your geometry and the types of products that you're trying to analyze. But I've just increased this here, so we've got 10 elements, so there'll be 11 nodes across the length of the part. Once it's set up, we can just hit run, and this should kick off, and it shouldn't take very long to run the analysis and give us our results. So 5 seconds or 5 to 10 seconds, and we've already got a result. We can, as I said before, we can look at the results and interrogate the results. So I can go and look at the von Mises stress and displacement. But like I said, we can really disregard those stress and displacement results, because the number that we're actually concerned with is the eigenvalue that comes back from it. And you can see here that we've got an eigenvalue of 0.945, which is suggesting to us that the failure, or the point at which the part starts to buckle, is at 0.94 times by our load. So our load is 10 kilonewtons. So you would expect that based on this study, buckling is starting around 9,450.926 kilonewtons. So this is the point of failure. So now that we've got that failure point, what we can do is go back in and start running our linear static study. So why do we run a linear static study? Well, we run a linear static study to determine whether we need to run a nonlinear study. That's really the reason why we're doing this. And so let's just step through the process of running the linear static study and determining whether we need to go any further. So I've created a separate new study inside the same part. We have assigned the same mesh, the same physical properties, the same load conditions and fixed condition. In this case, the load could be adjusted, so you could argue, well, the load really should be now 9450 because that's our buckling load, and we go OK, and then we can just simply run our study. Now what this is going to do is it's going to look at will give us our stress and displacement, accurate stress and displacement on the part. So I can edit and then display, I'll shift this across so that we can see it a little bit better, but display our stress plot. So you can see here we've plotted von Mises stress for our bar elements, and our maximum here is going to be 84. So we have a maximum stress of 84. Now, so the thing to keep in mind here is depending upon the value of our maximum stress can indicate to us whether we really should be looking at running a nonlinear analysis. In this case, our stress is around 85 megapascals, which is close to, like if we assume that yield of the material, and like I said before, we may be using a material similar to alloy steel here, we're getting close to maybe half of the yield of the material. So which is really the criteria that we could look at. If when we're getting around half the yield of the material in this case, then we should be considering looking at a nonlinear study to validate the results that we're getting. In this case, we're sort of getting around that range. We're getting about a third to a half of the value. So we might use that as an indicator to say, there is some concern here that the stress is high enough for us to then look at whether the part is going to buckle and in what ways it's going to buckle as well. So what we'll do is, now that we've established, yes, stress is a concern for us, we've got our stress, we can look at our displacement as well. So if we wanted to, we can plot our displacement and look how much the component is displacing. We might now then determine, yes, we need to run linear buckling and a nonlinear static analysis. So that's what we've done. We've set up a nonlinear buckling analysis, and we've pretty much done the same with the nonlinear buckling analysis as what we did with the linear buckling analysis. So we've got the same mesh settings. You can see in here we've got 10 elements and 11 nodes. We've got the same buckling material that we'd previously defined. The physical properties haven't changed. It's still the same physical properties in terms of the section size and the way that we've assigned it. We are using the nonlinear buckling load, which is slightly different in this case, only because we're going to adjust it in this instance, or if we wanted to adjust it slightly, we could. And we've got a fixed constraint at the bottom. And again, that's duplicated in a second subcase in the case of the buckling analysis. Beyond that, really, there's no additional steps that are required. So we can simply hit run in this case, which is going to run the analysis and quite quickly give us back some results. So you can see here it took about the same time as what the linear analysis, again, quite a simple study for us to be running, and we can see the eigenvalue associated with buckling. And because it's such a simple structure, we are seeing a very tight and close correlation with the results. We're getting 0.945096. So again, it's suggesting that based on our load, which is 10 kilonewtons in this case, we would expect that buckling is going to happen, or the critical buckling load is around 9,450 newtons. So what we can do from here is that we can then run a nonlinear static analysis and try and look at what's happening with the geometry as a result of this. Because now what we can do is, and this is the really interesting aspect of using the Nastran In-CAD product, is that not only can we determine the point of buckling, but we can look at the factors associated with what happens at buckling. So there are a couple of differences though in the way that we've set this up. So firstly, the mesh of the model. Again, you could use the same number of mesh elements in this case, so there's really no difference in the way that we could define this. Physical properties are the same, but we're still using the same material. We are applying the same load, we're applying a fixed constraint to the bottom, but there are a couple of things that I want to point out to you. Firstly, we have changed the nonlinear setup. Typically this would come in with 10 increments that it would be running, so it would be applying a tenth of the load, running the analysis, applying another tenth of the load, running the analysis, applying a tenth. So it can cycle through 10 times in 10 increments, running the loads and rerunning the analysis, each time recalculating the stiffness of the part. We want to increase the number of increments here because that buckling is happening very late in the application of the load, very close to the full application of the load. We want to make sure that we've got enough increments that in our analysis to capture what's happening at the end of when it is starting to buckle. The other thing that we're doing is turning on intermediate output. So by default this is turned off. By turning that on, what we're doing is we're telling Nastran In-CAD that we want to capture the output, the results from each of these increments, so that later on we can go back and interrogate them, look at the stresses, look at the strains, look at the displacements. The other thing that we've done is applied a kick load. And we talked about applying kick loads before. So why do we apply kick load? Well, if we don't apply a kick load, this part is idealized. It's idealized in such a way that it's almost flawless. You think of it. So the geometry of the part, it attunes that it's perfectly cylindrical or spherical. Cylindrical. It's got a 12.5 mil radius. It's exactly 250 mil long. It's exactly vertical. It's fixed perfectly at the base. The load is applied directly down through the center of the part, and it's applied exactly along its axis. So there's really no flaws in the design. So if you were to analyze the structure, we really need to be able to excite the buckling phenomenon associated with the failure of this part. So to do that, what we've done is we've applied a very small load, which is in the X direction. You can see the load here running out to along the X-axis. It's only a 5 newtons, so we've got a 10,000 Newton load down, but a 5 Newton load out from the part, just to give it a slight bit of load in that direction to help it just start that buckling phenomenon. So in this case, what we can do is we can run the analysis, which is quite quick and easy. Though having said that, it will take a little bit longer than what we previously saw. So if I bring across the nonlinear status bar that comes up, you can see here that as it's running through the increments, it's showing us each increment it's doing. Remembering we've put in 40 increments. One thing you notice that low in the range, the iterations that it's doing for each increment is very low. But notice what happens when it hits around that 35 to 40 increment where we start to see the part buckle. You're going to see the number of iterations increase. And what you're finding is because the part then is starting to fail as a result of buckling, the analysis is then, as a result, running through numerous iterations of the calculations at that point in time to ensure the accuracy of our results. So it's come back, it said that it's run through all of those. So what we can do is there's a couple of things. We can load up our results. So I'm going to load the results, say, at our 40th increment. Notice because we had the output results at each increment turned on, I've got 40 sets of results that I can look through, and I can now displace or display each of those increments. And you can see here that we've got at the increment 40, we've got extremely high stresses in that area. We can look at displacement and see how much displacement we've got at that increment. That's about 106 millimeters. So it's quite considerable, the change. If we go back to maybe, say, the 30th increment, so this would be about 75% of the load applied, you can see that our displacement is very small. It's 0.34 of a millimeters. So, between the application of our last 25% of our load, we are seeing significant displacement and as a result stress inside of our part. How can we look at this more diagrammatically? Well, you can go to our XY plot. So if you right click on that, and you can turn on the output to track the node. So I've clicked on the end node of our geometry here. I just want to track the movement of that in the X direction. So I can change the component from total to X and hit show XY plot. You can see here it's going to plot the displacement as a factor of the load that's being applied. And notice that we get up around here where we're applying 0.9% of our load, and all of a sudden it gets around sort of 0.915 before all of a sudden you see basically a catastrophic failure of the part where application of very little load is resulting in quite significant displacement of our part. Notice that that 5 Newton load that we applied is applying very little displacement. So it's so small that it's really almost negligible in the sense that it's not affecting or significantly affecting the results that we've seen. And you can see that through the displacement early in the load scale factor graph there. So what does all this mean? So let's go back to our presentation and have a quick look at the results that we got. So as a result of this, if you do the hand calculations, you're going to end up with a theoretical calculation of around 9,450 newtons as the critical buckling factor. If you run a Nastran In-CAD linear buckling analysis, you'll find that it's suggesting that the buckling should occur around 9,450 newtons. I think it was 9,450.9 newtons. So it's out by a very small factor, very close to the theoretical value. Likewise, if we do the same inside of the nonlinear buckling analysis, it gives us a very similar, if not the same number. Again, a very small discrepancy from the theoretical value. If we then using that, we run a nonlinear analysis and look at the graph and determine where the part is actually buckling and look at the geometry at that point in time, you'll actually find that the discrepancy is still, again, very, very small in comparison to the theoretical value associated with that. So again, very good correlation between all of our results there that we're gathering. Okay, so let's draw a quick conclusion around this. So hopefully this webinar has taken some of the mystery away from running a buckling analysis. We've shown that starting with a linear buckling analysis can give us the eigen-based buckling that we can use with a static stress analysis. And then based on the results of our linear analysis, we can then move into a nonlinear buckling followed by a nonlinear analysis to see the post-buckling response of our design. So let's just finish off the webinar before we look at any questions that anyone has. Some further reading if you're after some more information associated with the use of Nastran In-CAD. The forums are a fantastic place to go because you're going to get a lot of other people that are using Nastran In-CAD that are posting questions, ideas about ways to improve the product, communicating directly with some of the Nastran In-CAD team. So from a user's perspective, the forums are a fantastic avenue for you to use. If you're looking for some information about the latest happenings with Nastran In-CAD and some of our other simulation solutions, you'll find that the Twitter Autodesk account, simulation account, is a fantastic place to connect with, as is on Facebook, the Autodesk Simulation Facebook page, and YouTube also has an Autodesk Sim 360 channel, so another great one to follow. More locally, we have a Future of Making Things group on LinkedIn where we're talking about a number of technologies that are changing the landscape for manufacturing and manufacturers in Australia. Please, if you're on LinkedIn, follow the group. There's a lot of valuable information posted almost daily there. Again, if you have any questions, feel free to reach out to me. My contact details are on the screen there. If you'd like to talk to me after the session, don't be shy. Otherwise, let's have a look and see whether there aren't any questions. Not that I can see, which is a good sign. So hopefully all that made sense. So if that's the case, I'll wrap it up and we'll call it a day. But thank you for attending today's webinar. Have a great afternoon, and hopefully we'll see you next week. Bye for now.